My name is Tian, a PhD student from Hong Kong University of Science and Technology. Today, I would like to introduce our research, which introduces new privacy-preserving online learning framework named Sphinx. With Sphinx, we can upload our data to the cloud for machine learning training and inference services without exposing our user privacy. Nowadays, machine learning has become the fundamental infrastructure and core functionality for many applications. However, users have to upload their individual data to the cloud, which raises privacy concerns. Our goal is to provide a practical privacy-preserving online learning service over the cloud, where the user can incrementally update the model and perform prediction tasks without worrying about privacy issues. The online learning setting is as shown in the figure. The model should keep updated continuously with new training data and is able to perform real-time inference for user demands. During the procedure, the uploaded input data as well as the model all should be protected against the service provider. To ensure privacy guarantees, researchers have proposed a lot of privacy-preserving machine learning algorithms, either for training or inference. However, to the best of our knowledge, none of them can provide online learning capability over the cloud. Approaches for training either are inefficient or make extra assumptions, such as multiple non-colluding servers or a trusted third party. Approaches only for inference are fast. However, they generally assume a plain public model on the server, which is not available for training where the model parameters will be updated and need to be protected as well. To fill the gap between solutions with different cryptographic tools, let's take a closer look at previous approaches. On one hand, in order to protect the trained model, approaches for training use cryptographic tools to encrypt the model parameters. Thus, the model training and inference require arithmetic operations between encrypted inputs and encrypted model parameters, which is often slow. On the other hand, privacy-preserving inference approaches assume a public model stored as plain text in the server. Thus, they only need to consider to optimize the operation between encrypted inputs and plain model parameters, which is often faster. Therefore, there is a conflict between achieving fast training and inference and preserving model privacy. Our solution is to introduce differential privacy. Differential privacy is a privacy-preserving technique that adds random noise on data to confuse the attackers. Differential privacy protects messages without cryptographic methods and uses plain text instead of ciphertext. Thus, we found that it's a suitable tool to fill in the gap. If we can protect the model as plain text, use differential privacy, maybe we can bridge the two types of approaches together for an online learning solution. However, differential privacy also has its drawbacks. Current differential privacy-based measures assume a trusted data aggregator to add noise and have been criticized for its unsatisfied trade-off between model performance and privacy preservation. Specifically, attackers can infer the training data from the perturbed model gradients. Sphinx proposed hybrid protocols based on differential privacy and cryptographic tools to solve the above problems. It strikes a balance between model performance, computational efficiency, and privacy preservation. Here, let's see how Sphinx works. At its core, Sphinx divides each linear layer in deep neural networks into two parts and protects them with different privacy-preserving techniques. Given one input sample, the forwarding operation for each convolutional or fully connected layer can be formalized as this equation, where W is the linear weight matrix, B is the bias, and F denotes the activation function plus some extra function such as polling function. We call all the W in the model the linear components, and the B the bias components. Sphinx encrypts all the bias components with homomorphic encryption and perturbs the linear components with differential privacy. Therefore, the bias components stored on the server are ciphertexts, and the linear components are stored in noisy plain texts. This core feature enables fast training and inference protocol designs. As shown in the figure, the W in those white boxes are the linear components in plain text, and those biases in blue boxes are encrypted BIOS components. F denotes the activation and extra function. During the training procedure, the client will encrypt the training data and then send it to the server as the input of the first layer. And then, the forwarding and backpropagation procedures involve the homomorphic operations between the encrypted features and the two components. After the gradients are calculated, we send the encrypted linear gradients back to the client to apply differential privacy mechanism by adding noise. These noisy, decrypted gradients are then sent back to updated model parameters on the server. The forwarding and backpropagation operations are shown here. We can see with the W unencrypted, the homomorphic matrix multiplications between ciphertexts are replaced with multiplications between ciphertext and plaintext, which is several times faster and results in faster training speed. The server trains neural networks with stochastic gradient descent. It iterates on many batches of the training dataset to update model parameters. At each training step, the client takes a random sample batch with size B, encrypts and sends it to the server. Based on the input batch, the server computes the encrypted gradients following the forwarding and backpropagation formulas described before. For the encrypted BIOS components, the server can aggregate and averages the gradients locally and directly updates the model parameters. For the linear components, the server sends their gradients back to the client for decryption. The client decrypts them with the private key, clips the gradients, and adds Gaussian noise on the average gradients. The perturbed gradients are then sent back to the server to update the linear components. With the help of homomorphic encryption, we can apply differential privacy on the gradients without a trusted aggregator. The reason is that generally to add noise on aggregate gradients, we need a trusted data aggregator to aggregate the gradients and apply differential privacy noise, as shown on the left here. However, in our framework, the input data as well as the gradients are processed homomorphically and thus are not exposed to the server. Moreover, the differential privacy mechanism is applied on the client side. So only the perturbed gradients are exposed to the server, and we apply differential privacy without a trusted party, as shown on the right. We also design specific protocol for inference based on secret sharing. By storing the linear components as plain text, we allow the use of techniques used in previous inference protocols that were only available with the assumption of a public plain model. Here we give an overview of our inference protocol, which is split into two phases. The pre-processing phase is independent of the user input. For every linear layer, the client generates a random mask R, encrypted, and sent it to the server. The server generates a mask S and performs homomorphic linear operation to generate W times R plus B minus S and sends it back to the client. Now the two parties hold the secret share of W times R plus B. In the online phase, with the user input X, the client minus it with the mask R prepared in the preprocessing phase and sends it to the server. The server performs linear operation in plain text by only multiplying W. Notice that we don't need to add ciphertext B. Now the two parties hold the secret share of W times X plus B. The server then sends its share back to the client, so the clients can add them together to get the linear operation result. The online phase is free of homomorphic operation and thus can achieve very fast online inference response. The inference data is protected with secret sharing and thus has a higher privacy preservation level than the training data, which is partially protected with differential privacy. Moreover, we also propose several system optimizations for Sphinx to further accelerate the model training procedure. The first optimization is fast homomorphic multiplication. We use CKKS as our homomorphic encryption scheme, where after every ciphertext to ciphertext multiplication operation, rescaling and relinearization operations are needed to enable further multiplication. Sphinx deliberately refines the homomorphic operation behaviors for every operation in the forwarding and backpropagation phases to avoid or delay rescaling and relinearization as much as possible. The details are given in the paper. Second, right now, because homomorphic encryption cannot handle nonlinear functions other than polynomials, we need the client's help to evaluate the nonlinear activation functions. Because the activation function input and output in the forwarding phase are usually also needed again in the backpropagation phase to calculate the gradients, Sphinx adopts a forward propagation cache. In the forwarding phase, it calculates the gradients of the activation functions beforehand and stores them in the cache. These stored gradients are then directly used in the backpropagation phase to avoid duplicate computations and communications between the two parties. The final two small optimizations are called zero decryption and zero encryption. In the training protocol, decryption and re-encryption occur in every ciphertext sent to the client, either for nonlinear activation function evaluation or differential privacy mechanism. Because we realize that no more arithmetic operations are needed for these sent ciphertexts before decryption, we adopt zero decryption to reduce the level of these ready-to-be-sent ciphertexts to zero. Here, the level determines the number of homomorphic multiplication allowed, as well as the size of the ciphertext. So, by reducing the level to zero, we result in a much smaller ciphertext size during the communication. For the re-encryption part on the client side, we realize that homomorphic addition between ciphertext and plaintext is much faster than the encryption operation, as shown in the table here. Thus, Sphinx adopts an encryption method we call zero encryption. In the offline pre-processing phase, the client prepares a stream of zero ciphertexts by encrypting zeros, which works as one-time pass ciphertexts. So in the online phase, once the client needs to encrypt a message, it encrypts the plaintext by directly adding it with a prepared zero ciphertext, thus shortening the encryption time in the online phase. We have implemented the Sphinx with C++ based on the C lightweight machine learning framework Qiang. We use the CKK's HE scheme implemented in CL 3.6. We evaluated Sphinx on two famous datasets, MNIST and Cipher10, with two convolutional neural network architectures. For the privacy-preserving training, we compiled with pure homomorphic encryption training protocols. We found that Sphinx achieves 35 times less training time and 5 times lower communication costs for both neural networks on the two datasets than the pure homomorphic encryption method. For private inference, we compared with both pure homomorphic encryption methods as well as those private inference protocols. We found that Sphinx achieves real-time inference in the online phase, which is 4 orders of magnitude faster compared to the pure homomorphic encryption method, similar with private inference protocols such as Delphi. However, Delphi assumes a public plane model on the server. For the evaluation of differential privacy mechanism used in the training protocol, we draw the trade-off curve between model accuracy and the differential privacy level with different datasets and hyperparameters. We found that given the same privacy budget, Sphinx achieves a similar model accuracy as the pure differential privacy training algorithm without a trustworthy server. Finally, we use a practical reconstruction attacks to attack Sphinx and pure differential privacy solutions. The method tried to restore the input images from the noisy gradient. The results showed that even with similar theoretical privacy cost compared to differential privacy solutions, Sphinx can achieve a significantly stronger defense against practical attacks because it protects parts of the model parameters, the bias components, with homomorphic encryption against the attackers. Okay, so to summarize, we present Sphinx, a hybrid privacy-preserving online learning framework. Sphinx has significantly accelerated the privacy-preserving training and inference speed, thus enabling privacy-preserving online learning service over the cloud. The paper is online and we will release the code soon. So that's all. Thank you.
All right. Any questions? Please come up to the microphone.
Hi, Han. Nice talk. I'm Mingxun from CMU. So I wonder what's the sigma in your PPT, because generally we have like epsilon delta differential privacy, where epsilon is smaller, it means higher privacy, but in your slides it seems it's reversed.
You mean the delta? You mean in the differential privacy evaluation, the delta?
Yeah.
Could you repeat your question again, because I would say no delta here.
So what's your privacy parameters? So what does that sigma mean?
The sigma. The sigma here means because for differential privacy level, the original one, we only have epsilon, right? The epsilon parameter, but afterwards, later there's another differential privacy mechanism based on two parameters, epsilon and delta. So the delta means that there may be a small probability that the information will be leaked. So epsilon means the similarity between two distributions, right?
Yeah.
Delta means that is a very small probability that the two distribution may be totally different. So the details for the details, maybe you can refer to some differential privacy papers.
Okay. Yeah, we can talk that later.
Yeah.
Hello, I'm Mayank from UC Berkeley. I have two questions. The first one is that, is your approach not suitable for a setting where the server's model is proprietary and clients cannot see it? Because I think in your approach, you send back the gradients to the client, and client is responsible for adding the noise, and like client does the decryption, so client basically sees the weights and everything. So it kind of seems that it won't work in a setting where you have a proprietary model and you don't want to share it with the clients, right?
Yeah.
And then how do you compute activations over encrypted data? Like, do you actually change your model to make all the activation functions linear?
Yeah. Okay. So for the first question, so in our use case, because the model is updated by the data uploaded by the client, so here, in fact, we will assume that we do not protect the model against the client because all the data comes from the client. So so here here it's okay for our in our scenario for the client to see the gradients. So and for the second question, the activation here, in fact, is we use a client-aid model. So because we did not some researchers transform the activation into polynomials, but here we just use the original polynomial. We just use the original activation functions, and we and the server need to send this data back to the client, and the client will decrypt them and perform activations on them and encrypt them again and send them back to the server. And this is, in fact, and it will be improved if this problem of homomorphic encryption will be solved in the future. Yeah.
Yeah, cool, got it.
Hi, so nice talk. So I have a quick question. So looks like in your protocol, the client needs to be online during training. So do you have any numbers on how much computation the client needs to be done compared to if all the training was happening in client itself without doing any homomorphic encryption or differential privacy?
So you mean the converge time of the model?
So now the client is doing some computation during training. So the other scenario is, alternative scenario is there is no server at all, or the server is only doing some storage. So the training can happen in client itself, right, without doing any homomorphic encryption. So what's the time So compared to that computational time, we expect the client's computation time in this case should be smaller than the plain training on client itself, right?
Yes, in fact, it is true. But I think I do not have the data now. I think we have done that before, but we haven't put that kind of data in our paper because maybe you can send me an email and we can, send this data to you about
Okay, yeah.
the time.
Okay. Thanks. So, but it is also, so your case client is now computation is much lower than doing the training on the client itself, right?
Yeah, I agree with you.
Okay.
So yeah, but here because it's not our privacy concern, so yeah.
Okay. Thanks.
Alrighty, thank you so much for joining us remotely and for answering questions. So let's give the speaker
Thank you.
one last round of applause.